Welcome friends. In today's session we are going to discuss about one more network element, which is inductance. So friends, in the year 1820, Oersted made an important discovery that the needle of a compass gets deflected by the presence of a current carrying conductor, indicating that the effect was related to magnetism. Subsequently, Faraday found out that with two conducting circuits are in spatial proximity, a charging magnetic field produced by one circuit induced a voltage in the other circuit. This is the equation for Ohm's law for an inductor, that V is equal to L di upon dt. Friends, this is a very important equation and we will be solving many important questions with the help of this equation in upcoming sessions. You must note here that this di upon dt is the rate of change of current, instantaneous rate of change of current. This V is the voltage drop across that inductor, like IR is the voltage drop across a resistance. Across a resistance, if we see a voltage drop as per Ohm's law, it is I into R. So across a inductance, the voltage drop can be given by L into di upon dt, where this V is the instantaneous voltage across the inductor. It keeps on changing. That's why we use this term instantaneous. Across a resistance, all along the time axis, the voltage drop remains the same. That's why we call that resistance is a linear element, but inductance is a non-linear element. So this VL keeps on changing with time. That's why we call, whenever we consider the instantaneous voltage across the inductor. L is the inductance in Henrys. L is the inductance of that coil and the unit is in Henrys. Now this di upon dt is very important, because on this depends the instantaneous voltage across the inductor, because this L is constant and the voltage drop depends upon di upon dt, which is the rate of change of current. Friends, the rate of change of current, when it is 0, if di upon dt is 0, the current is not changing, then VL, voltage drop across inductance, is also 0. So voltage drop across inductance is only observed when there is a rate of change of current. When the circuit is stabilized and the current is a constant current is flowing in a circuit, then di upon dt is 0. That's why the voltage drop will always remain 0. Now friends, if we see a inductance, then we can put core in inductance. But if the core is air, less inductance will be observed by the same coil, and if the core is soft iron, then more inductance will be observed. It depends upon the permeability of the core. Now soft iron has a permeability of 600. That's why the soft iron core will induce more inductance. An approximation of inductance of any coil or wire can be found by this formula. Inductance is equal to N square. This is a very important formula. Inductance is equal to N square. N is the inductance of the coil in Henrys. L is the inductance of the coil in Henrys. N is the number of turns in wire coil. If the wire is straight, then we consider this N as 1. Mu is the permeability of the core, and A is the area of the coil in square meters, cross-sectional area, and L is the average length of the coil in meters. We'll use this formula in our questions. Now we can more closely understand this formula. If this is the coil, then L, the last L, this average length of the coil, is this length, the actual length of the inductance from here to this point. This is considered to be the average length of the coil, and N is the number of turns, mu is the permeability, and A is the area of cross section. Now friends, L upon mu into A, this can be given a new name called reluctance. So reluctance is defined as length upon permeability into area of cross section. So friends, this formula is very important as far as inductance is concerned. Now friends, L upon mu into A, this can be given a new name called reluctance. So reluctance is defined as length upon permeability into area of cross section. So friends, this formula is very important as far as inductance is concerned. Now let us understand a better look on the resistance of the coil. The resistance of the coil will depend on the actual length, and the actual length of the coil is not defined by small l. You can see here it is represented by capital L. This is the actual length of the wire with which the coil is being made. It is not small l. This is small l, but the complete length of the wire is capital L. And this area of cross section is capital A. Area of cross section is capital A. Now the time constant of the inductor becomes L, which is the inductance of the coil, upon R, which is the resistance of the coil. Let us take one example to understand it in greater details. A coil is divided into two equal parts. If tau is the time constant of the original coil, then we have to find out the time constant of the combination if two parts of the coils are connected in parallel. So friends, like this we have connected two half of this coil in parallel. Here in the figure you can see this half part of the coil is connected with this half part in parallel to each other. Now what we can see here is that the length, the physical length of the coil has become half. The inductance also becomes half, because inductance depends on this formula. From this formula we can easily calculate that the inductance has become half. Now number of turns also becomes half, because the coil has been cut from the center, and the resistance also becomes half, because coil resistance depends on the complete length capital L, and this capital L has become half. That's why the resistance has also become half. Now if we can see that equivalent inductance becomes L by 4, because equivalent inductance we can see from 1 upon L equivalent is equal to 1 upon L by 2 plus 1 upon L by 2. So this L equivalent becomes L by 4, and R equivalent also becomes 1 upon R equivalent is equal to 1 upon R by 2 plus 1 upon R by 2. So 1 upon R by 2 plus 1 upon R by 2 becomes 2 upon R by 2, or is equal to 4 upon R, and hence R equivalent becomes R by 4. So this L equivalent and R equivalent have been calculated, and these are L by 4 and R by 4. Now equivalent time constant we can find out from the same formula. It is always equivalent time constant is L equivalent upon R equivalent. So L equivalent is L by 4 and R equivalent is R by 4. So L upon R, the 4 gets cancelled with this 4, and the time constant remains the same as that of the original coil. Thanks friends, we will keep on discussing such important topics on this channel. So please subscribe Technitude. Thank you.